Okay, so diving right into this stack of pharmaceutical biotech materials, looks like we are tackling penicillins today.
Yeah, penicillins, really a classic,
Right.
one of those foundational antibiotic classes.
Definitely foundational. So, goal for today is to give a solid overview of what they are, the different types, how they actually work against bacteria.
And of course, how those bacteria fight back, that's always the big challenge, right?
Absolutely. Resistance is huge.
Yeah.
So let's break it all down.
Sounds good. Starting with the heart of it all, the structure. You'll see in the materials that every penicillin has this central thiazolidin ring.
Right. And it's fused to a beta-lactam ring,
Exactly. That beta-lactam is key for how they work.
like the engine of the whole thing.
Yeah, good analogy.
Mhm.
And attached to that, you have all these different side chains. Those are what make each penicillin unique.
So that's what determines which bacteria it can go after.
And things like how stable it is in the body. Small tweaks, but big effects. Now, how they actually work, their mechanism of action, they target these proteins called penicillin binding proteins, or PBPs.
PBPs. Okay. And what are those?
So those are enzymes that bacteria need to build their cell walls.
Cell wall is essential for bacteria.
Oh, totally. It's what gives them their shape and protects them.
So the penicillins basically mess that up.
Exactly.
Mm.
They bind to the PBPs and they stop them from doing their job, which is linking together these building blocks called peptidoglycans.
So the bacteria can't build a proper wall, then what?
Well, it becomes weak and eventually the cell just bursts. Bye-bye, bacteria.
That's pretty cool. It's like their Achilles heel. Now, let's talk about the different types of penicillins, because I know there's a bunch, right?
Yeah, for sure. You got your natural penicillins like good old penicillin G.
Penicillin G, so that's one of the original ones, I guess.
It is super effective against a bunch of gram-positive bacteria, streptococcus, things like that. Some gram-negatives too, and even spirochetes.
And those are,
Like the bacteria caused syphilis, for instance. But penicillin G, it's not very stable in acid, so you usually have to give it by injection.
oh, that makes sense.
Then there's penicillin V, which has a pretty similar range of activity, but it is more stable in acid.
So you can take that one orally.
Exactly. Big advantage there. And then you move into things like the immunopenicillins, amoxicillins, ampicillin.
Those names are familiar. I feel like those are prescribed a lot.
Yeah, definitely. They've got a broader spectrum. They can hit some gram-negatives that penicillin G doesn't. Things like Haemophilus influenza, E. coli.
Okay, those are some pretty nasty bugs.
Definitely. And they often get paired with a beta-lactamase inhibitor.
Beta-lactamase inhibitor, what's that all about?
So some bacteria, clever little things, they produce these enzymes called beta-lactamases.
Enzymes.
Yeah, basically proteins that can break down the beta-lactam ring in the penicillin.
Oh, so it's like the bacteria's weapon against the antibiotic?
Exactly. But by adding an inhibitor, like clavulanic acid,
That's an augmentin, right?
you got it. We can protect the penicillin and let it do its job.
Clever countermeasure, right?
Totally. And of course, there are the penicillinase-resistant penicillins, methicillin, nafcillin. Those were designed specifically to resist those staph beta-lactamases,
So that's what they use for staph infections.
particularly penicillinase-producing Staphylococcus aureus. But it's important to remember, not MRSA.
Right, MRSA is a whole other beast.
Exactly. And then you've got the extended spectrum penicillins like piperacillin and ticarcillin.
Extended spectrum, so they can handle even more types of bacteria.
Yep, they've got a wider range of activity, even hitting things like Pseudomonas aeruginosa.
And that one is...
A tough one to treat. It's often involved in hospital-acquired infections.
So it's like the big guns?
You could say that.
Mm.
And they're often paired with beta-lactamase inhibitors, too, like you see with piperacillin tazobactam or zosyn.
So we've got all these different penicillins, but then you've got the bacteria fighting back.
Always. They're constantly evolving, finding new ways to resist.
And beta-lactamase production is a big one, right?
Huge. It's one of the most common ways they become resistant. But there are other mechanisms, too, like altered PBPs.
Altered how?
Mutations in those proteins can change their shape, so the penicillin can't bind as well. A key example is PBP2A in MRSA.
So it can dodge the penicillin bullet.
Exactly. And especially in gram-negatives, you see things like reduced permeability.
Meaning?
It's harder for the drug to even get inside the cell. And then there are efflux pumps.
Those sound intense.
They basically pump the antibiotic back out of the cell.
Wow, bacteria are pretty smart.
They're survivors, that's for sure. That's why it's so important to understand how they resist so we can develop new strategies to fight back.
Definitely. And just thinking about where these drugs come from, it's pretty amazing that they're actually produced by a fungus.
Right. Penicillium chrysogenum, grown in huge fermentation tanks. It's quite a process.
So just to recap, penicillins target bacterial cell walls, and all the different types target different bacteria. But the biggest problem is resistance, with beta-lactamases and altered PBPs being some of the big culprits.
Definitely. And it makes you think, with all this evolution and resistance, what are the really new, groundbreaking approaches we're going to need to fight infections in the future?
That is the big question.
Absolutely. And that wraps up our deep dive for today.
Thanks for listening.